Good day, everyone. My name is Jonathan Thota, and I'm joined with my friend Shadmun Talukder Shahed. And our project is called Quantum Machine Learning for Malware Classification. And what we basically did was take a classical machine learning model, a support vector machine, and put it head to head against two quantum models on the same problem. The dataset we used is called CLAMP, and it's a malware dataset. So the task uh, we what we are trying to solve is figuring out whether a given file is safe or malicious. We picked this problem because malware is a real ongoing headache in cybersecurity, where bad files can wreck systems, leak data, and spread across networks. And the earlier you can flag malware, the better. So a good classifier here actually matters. So the question we wanted to answer was pretty straightforward. Can quantum models actually hold their own against a solid classical baseline? And if they can, what's making the difference? We ended up running 4 steps. First one was the classical SVM. Then the SVM trained on the exact same features as the quantum ones, and then the two quantum models, which were the QSVC and the VQC. Now coming to the roadmap. Uh, so we first started with the problem and what we were trying to do, then the data set and how we cleaned it all up. After that came the feature selection, which turned out to be the most important part of the whole project, especially on the quantum side. From there, we get into model comparisons, and then we'll wrap everything up with the results, what we took away from it, and what we do differently if we had another shot. So the to set this all up, every row in our dataset is an executable file, and every column is a numerical attribute that is pulled out of that file. So the job is to find patterns in those numbers that separate malware from your regular software. And the goal wasn't just throw some models and see what sticks. We built out an actual pipeline from loading the data, cleaning it, picking features, scaling them, training the models, comparing the results, and we even put a small inference layer at the end so that the trained models can be reused on new samples later. We tested 4 setups in total. The first was a classical SVM on an earlier feature set, which didn't do well. Uh, we'll explain why later. The second was a fair classical SVM, which was trained on the same features that the quantum models used. So the comparison between this model and the quantum models would be uh, apples to apples. The third was the QSVC, which uses a quantum kernel, which is basically a quantum way of measuring how two samples are similar. And the fourth was the VQC, sorry, which works like a small quantum neural network. So coming to the workflow, this uh, this is the workflow we used. We started by loading the clamp uh, CSV, which is around 5,000 5,184 rows, each one a software sample with a label telling us if it's benign or malware. Once that's in, we clean and inspect it. We drop the columns that are empty or aren't useful, and check for um, missing values. This step matters very much because if skipped, we can end up with models that look great on paper but are learning from garbage. Then we come to the feature selection, where we used correlation analysis uh, to find the features that actually relate to the label, and we cut the data set down to four of them. We cut them down to four because quantum circuits get expensive fast. Uh, the more features you have, the more qubits, the bigger the circuits, and the slower everything runs. So you really want to be tight with your feature count. Once you got our features, all the models train on the same reduced data and the same train test split. Uh, uh, After training, we compare them using accuracy and confusion matrices. And then at the end, we wrap the best one in an inference layer with input validation and readable output. That way, it's not just a one-shot experiment and it can be reused down the line. Coming to the data set, the data set we used is called the clamp raw 5184 CSV. The target column is just called class, and after cleaning it, we ended up with 5184 rows and 52 columns. One thing that was nice about this data set is once we dropped the empty columns, there were no missing values at all. So we didn't have to, mess with the data too much, and we could just go straight into just go straight from cleaning into feature work. Uh, the class distribution is also pretty balanced, where we had 2683 malware samples and 2501 benign, uh, which really matters because if the data set is like 90% one class, a model can just predict the majority every time and still be accurate. So with a balance like this, the accuracy number we report at the end actually means something. So for the actual cleaning, the cleaning steps, we dropped a couple of metadata columns like E magic and E CRLC when they showed up, got rid of any fully null columns, double checked for missing values, and confirmed the class distribution. Uh, after all, After all that, we had a clean, reliable foundation to build the rest of the project on. So this is the feature selection. This is where the project actually gets interesting because feature selection isn't just a pre-processing step. It's a design constraint. In classical ML, you can usually get away with throwing a ton of features at a model, but with quantum, every feature you keep maps to an input on your quantum circuit, which means more qubits, uh, deeper the circuit, and longer the simulation times. So feature reduction is an integral part. And what we did was use correlation analysis to pick four features that had the strongest relationship with the class label, which were subsystem, major linker version, image base, and section alignment. These four gave us enough signal to actually learn from without blowing up the cost on the quantum side. So this is the quantum ready data preparation, and this is how we prep the data specifically for the quantum side. Even though the data set had over 5,000 rows, we only used 200 for the quantum experiments, where 100 were benign, 100 were malware. The reason for this is that QSVC and VQC both involve running a quantum circuit a lot of times, and on a simulator that gets really slow really fast. So 200 samples let us actually finish the experiment in a reasonable time. while still being able to, while still being big enough to compare the models in a meaningful way. So we split these 200 into 160 for training and 40 for testing. And we used a stratified split, which basically means just the class balance stays the same in both halves. So 80 and 80 for training, 20 and 20 in test. The last thing we did was scale the features. And this part is really important because quantum feature maps work by uh, encoding numbers as rotation angles on the circuit. If your features are on wildly different scales, these rotations come out distorted and the model basically ends up learning from noise. So scaling makes sure each feature actually pulls its weight.
All right, thank you so much, Jonathan. I really appreciate it. So, my name is Sadman, and I'm going to be continuing on with the presentation on our thing. And so here we are in the slide that is for initial classical baseline and basically what went wrong. So here we'll be explaining the initial classical SVM baseline for ours. The first SVM used an earlier set of the four features that we've mentioned or my colleague has mentioned before. And so this model was tested before moving to the correlation-based selected features. So now as you can see that it becomes quite obvious that the result was weak. And the initial classical SVM achieved only 51.98% accuracy. And so if you do like a deeper look into the confusion matrix, the issue becomes quite clear, which is that the model predicted almost every test sample as class 1 or malware. That means that it did very well when identifying the class 1 or malware, but it almost completely failed in recognizing class 0, which is the benign. And so this type of result is important because accuracy alone does not tell the full story. Even though the model was slightly above 50% accuracy, it was not truly learning a balanced decision boundary as we see. It mostly leaned towards one class, and in malware classification, this kind of behavior is risky just because a model that ignores one class cannot be trusted in a real security setting. And so the main lesson we can gain from at least this slide is that the poor result was likely caused by weak feature selection. And SVM method itself was not necessarily the problem, but this is why the next step for us was to create a fair classical SVM baseline using the same top four features that my colleague Jonathan has mentioned that was also used in the quantum models itself. And so we're going to be looking at, as I've mentioned, the fair classical SVM baseline. And here we present it right here. And so this model uses an RBF or a radial basis function kernel that was trained on the same top four selected features that were used in the quantum models that we're going to be mentioning later on. Now, this is important because it creates a fair comparison, right? So any quanta, if let's say like, for example, a quantum model and a classical model uses the same feature information, then the differences in performance are more likely related to the modeling approach itself rather than the input data. So that's why we made sure that the input data and everything else was the same as it is. The performance improved significantly as we see over here. The fair classical SVM model achieved an 82.5% accuracy. In the confusion matrix that we can see here as well, the model correctly predicted 13 out of the 20 class 0 samples or the benign samples and 20 out of the 20 of the class 1 samples or the malware samples. This made 7 mistakes where class 0 samples were predicted as class 1, but it made no false negatives for class 1, which is a good thing. Now, this result is much stronger than the initial classical SVM that we've mentioned before. And the accuracy increased from 51.98% from the previous one, now up to an 82.5%. And this confirms that the original failure was mainly due to the poor feature selection itself and not the SVM algorithm. And so this slide itself is quite important because it establishes a serious sort of a classical baseline. And now it's time for the quantum models. And so it's important to make sure that the quantum models should not be compared only against the weak model, but they need to be compared against the classical model that uses the same selected features and have been prepared fairly. And so going forward, we'll be comparing the quantum models with this fair classical SVM baseline. And so here we are going to be presenting our quantum support vector classifier, or the QSVC results. And this is our first quantum model. Now, the QSVC for here uses a quantum kernel to compare samples in the quantum feature space. And for our project here, the QSVC applies a ZZ feature map with 4 of the input features that we mentioned previously. And so to go a little bit into the sort of ZZ feature map real quick, we know, as some of you guys, if you're familiar with quantum computing, you might be aware with the data encoding system for Z feature map. Now for a Z feature map, let's say it's a one-to-one comparison. So let's say, for example, you're a student, and for you, it's important to perform well as a student. And so there are many features that go into this. So for example, if you're a student, you may rely on sleeping well. You may rely on eating well. So you can map one-to-one features. So how does sleep correlate with your performance or your results? How does your food or food habits compare with your results as a student performance? A ZZ feature map, however, includes this concept of entanglement, where now you're having to compare between multiple variables. So here you're going to be comparing your sleep to your food. So let's say you have 100% good sleep, but you had a 50% of good nutrition. Then how does that impact your result? What about if your nutrition is perfect, 100%, but you have very poor sleep? Let's say you have 20% in sleep. Then how does that now affect your results? So it does this sort of many other different feature comparisons with what we have right here. And so the role of the quantum kernel is to estimate similarity between these samples after the data has been encoded into the quantum states. And so as we see over here in the results section, that the QSVC achieves a 92.5% accuracy, which is the highest overall result that we've achieved in our experiment. The precision was 100% for class 0 and an 87% for class 1. And the recall was an 85% for class 0 and 100% for class 1. Again, class 0 is benign and class 1 is malware. So the confusion matrix shows, as we see over here, that the model correctly predicted 17 out of the 20 of the class 0 samples and all 20 out of 20 of the class 1 samples. It only misclassified 3 of the class 0 samples, or the benign, as malware itself. And it made no false negative predictions for class 1. Now, this is especially important in malware classification because missing malware can be more dangerous than incorrectly flagging a benign file. And so now in this test set itself, the QSVC did not miss any of the class 1 samples. And so this makes the result very meaningful from a security perspective. And now, I guess if we were trying to sort of do an interpretation over here, which will be that the QSVC captures useful nonlinear relationships, as you said with the ZZ feature map, in the reduced feature space. Since quantum kernels can map data into different feature spaces, the model may find separation patterns that are harder for like a basic comparison model to capture. Now, under the constraints of our experiment itself, the QSVC is basically the best performing features. But so now let us look a little bit more into the other quantum thing that we wanted to look in, which is the VQC, or the variational quantum classifier. And so here we present the VQC, which is that it is now different from the QSVC because it uses parameterized quantum circuits that is trained on using an optimizer. And in our project, the VQC does use the ZZ feature map for data encoding, but it uses ansatz with 3 repetitions. Now, an ansatz, for those of us who don't know, so ansatz derived from a German word which is basically estimation. And so what it would do is, as we see in quantum computing, a lot of it happens with, we don't basically go with a classical approach where it's zeros and ones, but rather we estimate, or basically an educated estimate on what the output would be. And what this does is a good thing to a good approach, or a good benefit to this, is that it would require less resources in order to execute. So instead of going through each and every one of the data set and finding an eigenvalue to map onto it, it basically does an estimation or an ansatz, and that would actually help us reduce the cost of computation far more, right? And so that's how you're able to approach it. So now in our project itself, as you can see, is that it has achieved a result of 75% accuracy. The class 0 recall was 70%, and the class 1 recall was 80%. And sort of the macro F1 score here is 75 or 0.75, or basically 75%. The confusion matrix, as you see over here, is that the model correctly predicted 14 out of the 20 of the class 0 samples, or the benign, and 16 out of the 20 of the class 1 samples. So it misclassified 6 of the class 0 sample and 4 of the class 1 samples. And now, basically what this result shows is that the VQC was able to learn useful patterns, but it did not perform as well as the QSVC or the fair classical SVM model, as a matter of fact. Now, the reason is because the VQC performance can be sensitive to training choices. The optimizer, the circuit depth, the number of iterations, the ansatz design, and the initialization process itself can all affect the final results. So it's very sensitive, the VQC model itself. Another important information that I would like to point out is that the VQC is a trainable quantum model, so it may require more tuning to reach a stronger performance than what we've done. And so the results is still useful because it shows that the VQC can produce a workable classifier. And so therefore, maybe future work within this whole field can definitely improve the performance itself. But it also shows that the quantum kernel approach is more reliable in this specific experiment that we have. And so here we basically presented our model accuracy comparison over here. And basically what we can see here is that the one that is number 1 is basically our initial classical SVM that had the lowest performance. The second one is the one that we've just mentioned, the VQC. The third one is our fair classical SVM that we've done with feature selection. And then the greatest or the highest accuracy percentage is the QSVC over here on the right-hand side, rightmost side. Now, what we see with the first key insight is that the feature selection was sort of the turning point itself. When the SVM used earlier feature set, it performed poorly. When it used the top 4 selected features, that's when the accuracy dramatically increased, right? And so that feature selection itself is very important itself. The key insight too is that the QSVC has reached 92.5%, outperforming both the classical and the VQC. We're not really comparing too much with our first initial approach, just because that was just to show that an initial classical SVM would look like without that selecting features. And then the last one is going to be that the VQC showed usable performance, but it really depends on how we are going to train it or how to approach the different model itself. And so maybe a more tuned approach would be much better to then maybe use that for future usage within our project itself. Now, these are just some utilities and deployment readiness that we've done as part of our project. We included these features itself. Now, an important goal of our project was to make sure like the workflow itself was reusable rather than just leaving it as like a one-time experiment kind of a thing. And so we made sure that there was an inference bundle itself. Yeah, I apologize. I want to make sure that the inference bundle itself includes a trained model, selected feature names, fitted preprocessor, and label map. We did input validation as well. And last but not least, we did a readable output and error handling. Just so like if you're able to upload the data itself, we worked on that, but also in order to do easy mapping, like with class 0 and class 1. So for humans, it'll be easier to understand. So it'll give them a better understanding of the whole model itself and also the type of data we're working on, et cetera, et cetera. And so in conclusion, our main takeaway is that the QSVC achieved, as we see here, the strongest result with a 92.5% accuracy. This suggests that the quantum kernel model can be effective for malware classification when the feature space is carefully reduced and the experiment is designed with quantum circuit constraints in mind. However, there are also important limitations, right? Like with quantum experiments used only 200 samples, And even though the data set itself has, well, like 5,184 rows, um, this was done sort of to control circuit cost, but it means that the results should be interpreted as an experimental comparison rather than a final production level chain. My colleague and I, Jonathan and I, we basically were working with limited qubits, of course, as students, as whatever was available to us. And so we were thinking that perhaps with more qubits, we would be able to improve the results far more into the future. Now, the VQC performance may change with different optimizers, ANSAT design, and iteration limits. As I've mentioned just now, like it would depend on, of course, the qubit size, as well as maybe there are different ANSATs designs that we were looking into, and that those would definitely be able to improve the performance going forward. Now, the future work would be to test larger data set subsets, or a full data set. We were thinking of looking at this one OMAL data set from 2025 previously. However, that was very, very large. And so we were not able to run it through. And so that's why we decided to use this malware data set itself. We would maybe explore dimensionality reduction before the quantum modeling. And so that could improve. We wanted to compare alternative feature maps and kernels, like I said earlier as well. ZZ feature map is there, which is a very popular data encoding method, and at least the one that we were seemed very promising to us. However, there's also a poly feature map that you can basically tweak it to your own preferences, and so that might yield different results as we're going. And so, yep, like I said, to conclude, our project here shows that the model performance depended heavily on the feature quality itself. The fair comparison showed that the QSVC was had the best performance under these project constraints, while the VQC remained a promising model that may require further tuning. And thank you so much. And with that, if you guys have any questions, maybe you can leave comments, or please contact us and we'd be happy to answer it.
Amazing.